All right, welcome. Let's take a look at the WebAssign from section 5.4. So this is the section on work. So looking at the first question here, how much work is done in joules when a weightlifter lifts 160 kilograms from 1.5 meters to 2 meters above the ground? The important fact is that the lifter has increased the distance above the ground by 0.5 meters. Well, take the 160 kilograms, you're gonna have to convert that into newtons so that we can get a force of gravity. But once we get a force of gravity, we multiply by the 0.5 meters, the amount of the lift, and then the force times the distance will be the work. So this is just a basic force times distance computation, albeit with the initial weight given, in fact, in mass. 160 kilograms, you got to convert that to a weight to start. Number two here, we've got a variable force, 2x to the minus 2 pounds that moves along a straight line when it's x feet from the origin. So this force is only valid when we are exactly x feet from the origin, which means this force would only be valid for a very small change in x if we were considering the work that would be associated whenever we would be going from 1 foot to 12 feet. So plug in 1 here, you'll get 2 for the pounds of force that would be on an object at x equals 1. Well, that is only valid like very, very close to x equals 1. But we can actually just then integrate this f of x force function times dx, dx being the tiny change in x associated with the work in the proximity of x equals 1, and do that all the way from x equals 1 to x equals 12. So to do that, we would have to integrate over our region of interest. So we essentially just want to integrate the force function dx, because the force would be, the force and the dx would be the distance, and then the force times the distance would be your work. Integrate your work between 1 and 12. That would give you the total work over that time. So this is an integral from 1 to 12 of 2x to the minus 2 dx. Nothing too wild or crazy. Here is that same idea, although in graphical form. So we've got a force function. On the vertical axis, we've got the distance function on the horizontal axis. Force times distance would give us work. And so the area under the curve is going to be a measure of the work. So how much work is there between 0 and 12? Well, that's going to be dependent upon how much area was under the curve between 0 and 12. Right. So now, what do we got here? We got a heavy rope, 30 feet long, 0.6 pounds per feet is the linear density there. So you could multiply 30 times 0.6 to have an idea of how heavy the weight was in total. But yeah, the important thing is it's hanging over the edge of a building 80 feet high. How much work is done by pulling the rope to the top of the building? Well, I think if I'm conceptualizing this correctly, the 80 feet high of the building is actually not going to be relevant here, because what we're really focused on is the 30 feet of the rope. So you can imagine the rope sort of peering over the edge. And what we can do is just sort of break the rope into individual bite-sized pieces, where each piece is just, let's call it a delta y tall. I mean, maybe WebAssign prefers using x here if we walk ourselves through the tutorial, I'm not sure. But if you imagine each little chunk of rope being a delta y tall, then in terms of the number of feet, if you took delta y times 0.6, you would now have the weight, because this is pounds per feet. Pounds is a unit of weight, a unit of force. The 0.6 pounds per feet times dy would be the force of gravity on that little bit of rope. And then you have to figure out how far that little bit of rope has to be pulled. Well, if you view the top of the rope as, let's say, y equals 30 and the bottom of the rope as y equals 0, then that little bit of rope would have to be pulled 30 minus y, a distance of 30 minus y, right? Because if we were down at the bottom of the rope at y equals 0, we'd have to go 30 feet. If we were at the top of the rope at y equals 30, we'd have to go 0 feet. And so if you took the 0.6 dy times 30 minus y, that should give you the result. Now, if WebAssign frames it all from the ground level being y equals 0, now our rope would be between 50 and 80. And the amount that our rope would be pulled would be 80 minus y, where y is some number between 50 and 80. So in that case, if we use the distance to be 80 minus y, we would be integrating between 50 and 80 as opposed to between 0 and 30. So I'm not exactly sure how this tutorial breaks it down, but the basic idea is we want to break the rope into tiny little bite-sized pieces and then consider what is happening to each of those bite-sized pieces, integrating over where all those pieces live to determine the integral associated. Okay, we got a chain lying on the ground 10 meters long, mass of 80 kilograms. Okay, well, this now gives us 8 kilograms per meter for the linear density of the chain. And how much work is required to raise it, okay, to a height of 4 meters? Well, at that point, then you could imagine the chain at the final state between 0 and 4. So looking for, with respect to the final state, every little bit of chain would have been lifted some number of meters between 0 and 4. So here we're going to be integrating between 0 and 4. Each little bit of chain would be like a dy tall, a dy number of meters tall. Well, then if you took that number of meters times 8 kilograms per meter, that would give you, 8 dy for the mass of that little bit. Take 8 dy times 9.8. Now you've got the force of gravity on that little bit of chain. And then you multiply by y, because that's how high you would have lifted it. If y was 1, you lifted that bit of chain 1 meter. If y was 4, you lifted that bit of chain 4 meters. And so what does that turn out to be? That turns out to be like 8 dy times 9.8 times y within your integral, and we're integrating between 0 and 4. Okay, next, right, we've got a circular swimming pool, diameter of 10 feet, right, sides are 5 feet high, and the depth of the water is 4 feet. So if we imagine the circular swimming pool diameter of 20 feet, the radius there is 10, and so the volume of the water in here could be computed using what pi r squared times h, where h is the height of the water. Now, what we're going to do, since we are going to be integrating how much work it takes to pump the water, is we're going to be looking at one slice of water. So between 0 and 4, the depth of the water initially, call the bottom of the water y equals 0 and the top of the water y equals 4. We're just going to pick one slice of water. Now, that slice of water is going to be very thin vertically. It's going to be a dy thin. But then how big is it going to be around? It's going to be a pi r squared around. Right, because like the area of the water of that slice would be pi r squared. Take pi r squared times dy, that would give you the volume of the water within that slice. So in this case, that would be 100 pi dy for the volume of the water within the slice. So if we took the volume times 62.5, that would now give us a number of pounds, which would actually be the force of gravity upon that water. So take the 100 pi dy, multiply it by 62.5. Now you have the force of gravity on that slice. How far does that slice get lifted? Well, to be lifted out of the pool, it's got to be lifted up to a height of 5. So if that slice was at a height of y equals 1, you'd have to lift it 4 feet. If that slice was at a height of y equals 4, you have to lift it 1 foot. Regardless, you have to lift 5 minus y feet for every slice. So putting it all together here, we would have 100 pi dy times 62.5 to get ourselves the force, times 5 minus y to get ourselves the work associated with that slice. And now we're going to integrate between 0 and 4, because that is where all of our slices of water live. Okay, going down here, okay, let's see, how many do we, oh my gosh, we got 3 more. Let me pick up the pace here a little bit, I suppose, although this is the most challenging of the exercises. The idea here is that this basin, every slice of water, looking at with respect to verticality, because that's what you do whenever you're considering work, right? It's how much work is required to pump against the force of gravity. Each slice here is just a rectangle. Each rectangle is going to have the length of this basin, so that's going to be constant. Each rectangle is going to have just a dy of height. But now what is the width going to be? Well, that's going to be dependent upon the y, right? At y equals 0, the width is 0. At y equals 5, the width is 5. You can see the width 5 being here. But now, what would be the width of each slice? Well, that would actually be, given the height and the width are in exact proportion with one another, using similar triangles here, the height and the width are in a 1-to-1 ratio, which means that for a height of y, the width of that slice would be y. So you would take this y times 18 times dy would be the volume of each slice. So y times 18 times dy, volume of each slice. Then you take the volume of each slice times the kilograms per meter cubed, the density, to get yourself your weight of each slice, or your mass of each slice, multiply by 9.8 to get the weight of each slice. Once you have the weight of each slice, then you need to figure how far you have to lift it. Well, you got to lift it up to a height of 7 And down at the bottom, we started at y=0. Up at the top of the water, we were at y=5. At y=5, you have to lift 2 meters. At y=0, you'd have to lift 7. No matter what your y is, you'd have to lift 7 minus y units to pump it out. And so piece it all together here, you would have, let's see, 18 times y times dy times 1,000 times 9.8 times 7 minus y. And you would be integrating where all of your slices of water live, which would be between 0 and 5. At that point, you would be computing the work associated with pumping each slice of water between y=0 and y=5, which would be pumping the entire tank. So lots of work there, no pun intended, but well, here we are. Right, and we got a particle located some number of meters from the origin. This is very similar to the second question that we saw, where we have cosine pi x over 3 newtons that is acting on it as a force for any given x. Now this expression is only valid at the particular x, which means if we're considering the work associated with this force, that's only going to be a valid force for a very small change in x, right? As you change x, you change the force, which means you're essentially changing the work. So we have to essentially think of this force times a dx being our work, and then we're just going to integrate between 1 and 2. I think when you integrate this, you end up getting 0 because between cosine pi over 3 and cosine 2 pi over 3, the cosine function is symmetric about the horizontal axis. Don't quote me on that, but I'm pretty sure that's how it plays out. Right, a cable hangs vertically from which it's located at the top of the building. The work required for the winch to pull up the top half of the cable is half of the work required to pull up the entire cable. Physically imagine that, and that is definitely false. The first half of the cable is way harder to lift because you're lifting the entire mass of the cable initially and like 75% of the mass eventually, and then half of the mass. The last bit of the cable is very simple because at most you're only lifting half of the mass. On average, during that last half of the period, you're only lifting what on average, like a quarter of the width, a quarter of the length of the cable. Whereas during the first half, on average, you were lifting like 3/4 of the weight of the cable. So there's a lot more work on the first half than there is the second half. I guess 3 times more based on that analysis. So there we are. We've gone through the 5-4 WebAssign. Let's call that a discussion. And well, good luck.